Welcome everyone. I'm William Bloom. I'm from the Springfield team. I don't often get the chance to introduce invited speakers, so for me it's really a great honor and privilege to welcome Professor Neil Jones to Microsoft Research today. Neil is an emeritus professor of computer science from the University of Copenhagen. And as you know, Neil has a prolific academic career with more than 200 papers, 10,000 citations, and research that focuses on various areas of programming languages, computationality, computational complexity, computability. He worked on compilers, program transformation, program analysis, and semantics. And he's particularly well known for his work on partial evaluation, for which he wrote a book called Partial Evaluation and Automatic Program Generation. He's also made some important contribution to the spectrum problem, which is related to the P equals NP question. I personally first got involved with Neil 13 years ago when I did my master's thesis on size change termination. So size change principle was invented by Neil. It's a way to perform termination analysis on functional program. I actually almost did my PhD on that very same topic. There are a number of connections with Microsoft Research. Nicola Bjorner, who is here with us today, reminded me the other day that he took classes on category theory as a student at DICU, taught by Neil. He also reminded me that Yuri Gurevich, who is, I believe, a good friend of Neil, did some work on abstract state machine that rely on the constant time factors result by Neil. Also the work that Neil did on size change principle inspired a little bit the work of Byron Cook on termination analysis that was done here at Microsoft to prove termination of Windows device drivers. And finally, I found that Peter Lee, our corporate vice president at Microsoft Research, in his early career as a researcher, was actually working on partial evaluation. And so the second paper in his bibliography was on an implementation of parameterized partial evaluation with a number of references to Neil's work. Even though Neil is officially retired, he is still very much active academically. His most recent works includes compiling untyped lambda calculus to lower level code using game semantics and partial evaluation. And he told me he's also working on a paper on biomolecular computation on blood cancer research and genetics. And so that's something that I'm personally interested to learn more about. So without further ado, please welcome Neil Jones.
Thank you. I think I may have to work hard to live up to that introduction. Okay. I've had two parallel lines for many, many years. On the one side, writing compilers to make a living, and on the other side, doing theory in order to convince the university to give me a PhD degree. And eventually, through the years, these threads have merged and separated and merged and separated. And this is something that is, in one respect, a very theoretical paper, but it definitely has programming motivations. And I think it may say something to the programming languages. And you can see for yourselves as we go along. The other thing is the bulk of the work I'm describing was done around the turn of the millennium. And I figured that I had done a complete definitive characterization of everything that could be said about con-free programs and complexity. And then just this spring, somebody came up with something completely new. That I won't say it turned what I'd done on my head, but it certainly gave a very different perspective to it. And I'll mention that briefly at the end of the talk, done by Cynthia Copper, postdoc at DICU. In any case, the starting point is that we're all computer scientists. And the main job a computer scientist has to do is if somebody gives them a specification of a problem, then we have to produce a program that solves that problem. And it's this relation between problems and programs that I'm interested in. And an archetypical example is sorting. Now, there's only one sort function. It takes a list of integers as input and produces that same list in sorted order. Whether you're talking increasing or decreasing doesn't matter. But if you apply sort to some of the digits of pi, then you would get another sequence. So that's a well-defined problem. What about the sorting program? Well, there's an embarrassing variety of sorting programs. There's insertion sort, bubble sort, cell sort, shell sort. There's many of them. They're hard to compare. People have even written papers with taxonomies of sorting algorithms and trying to derive the one from the other. But the point is that these are solutions, and this is the problem. Now, going a little into that in a little bit more detail, once we know what the problem is, say if a mathematician or a user has given us the problem, then we have to figure out an algorithm for solving the problem. That's usually back of the envelope work, informal. Then that algorithmic solution has to be expressed in some program form. Once you've got it in program form and got it debugged, then you need to decide, is it good enough? Is it fast enough? Does it use too much space, etc. And if it's unsatisfactory, then we'll go back in the loop and try to come up with a different program or write the program in a different programming style, or maybe choose Prolog instead of Scheme, or in the worst case, come up with a completely different algorithm. But say if it's GCD, greatest common divisor, then you may end up changing making the change at this last level, because there are 100 ways of doing GCD, and there's many different factors. Now, what this talk is about is what effect does the programming language, or the style in which we write programs, have on which problems can be solved and how efficient they can be. And there definitely are effects there. I think part of this talk came from a conference called Express, and the focus was on expressivity. What is the problem-solving power of a certain language construction or a certain program style? And in the first place, power is a very vague word, but you can talk about absolute comparisons. Is there some problem that can be solved with feature X, but cannot be solved without feature X? Does your program have loops or not? That would be make a significant difference. Or you could talk about a relative power. Is some problem solvable both with and without this feature X that we're talking about? But any solution without X is necessarily less efficient than the same solution with X. These are not really the same. The first one is essentially mathematics. The second one, well, you can think of it as mathematics, but it's somehow much closer to the daily practice. And so there are paradigmatic questions. For example, are functional programs inherently less efficient than imperative programs? And this is very relevant, for example, to the discussions between Yuri Gurevich and Yanis Moskavakis, because Gurevich leans very heavily towards the imperative style, and Moskavakis leans very heavily towards the recursive style. And they both have very good, strong, well-developed arguments in favor of their view. But the kind of question I would ask was, are you tying your hand behind your back if you're only using the imperative version? And it's a question, and you have to make it more precise to be able to give an answer to it. One thing, a community I come with is very largely functional programming. And functional programming, well, on one side it's defining meanings by sets of recursively defined functions. But then also people get excited when they say if in a definition f of x, y equals if x can itself range over functions. Then if you have functions as arguments, then this, well, if you go to any POPL conference, you will hear many talks about the glories of higher order functions. And finally, the last one is a little more sober, but a number of people have strongly supported having strongly normalizing languages in which every program terminates, regardless of the evaluation strategy. And a natural question there is this tying your hand behind your back? Are there some problems that you can't solve, that you cannot solve in such a restricted language? So these are some of the kinds of questions that I'm finding interesting. So taking a little more into detail, we can say a programming language L is more expressive than a language M. And, well, an extensional view of it is saying that every M solvable problem is also L solvable. But there exist some L solvable problems that are not solvable by any M program. You can also ask efficiency. If you say that every problem solvable by M can be solved by an L program, and some can be solved faster than by any M program. And that's these are beautiful results. They're the kinds of things you really like to see, but you don't see them very often. They are very, very hard to prove. They're hard to formulate in the first place, and when they're formulated, they tend to go into this enormous array of unsolved open problems that are known in the complexity theory community. So I'm trying to make some progress on this glacial front between specifications and programs. Mostly, what I just talked about was extensional approach of saying the programs, what programs can define are more limited in the one language than in the other. An intentional approach is for looking at questions of the running times or the space or the factors that describe how the program runs. And one way you can compare programs in two languages is to write a compiler from the one language to the other. And this has something about expressivity. If that compiler can be written, then there is definitely a relation between the complexity of the two languages. You can also, this is translating programs as a whole. You can also relate computations, and of course the concurrency people have done a lot of this, things like small step simulations and more general simulations and bisimulations, and it goes on and on. And there's been much good work done on that. And here again, you can say that L is more expressive than M if every M program can be simulated by some L program, by whatever your current definition of a good simulation is. A more extensive, ambitious extensional version of this would be that this expressivity holds regardless of how you write your programs. And again, now we're skating very close to the halting problem and program equivalence in many undecidable problems. But this is mainly just to show that there is a spectrum of possibilities here. Now, there are obstacles to studying expressivity. There are good reasons why expressivity is a hard subject. One of them is Turing completeness. Any programming language worth its salt is Turing complete, at least in my opinion. Not everybody agrees with that, but I have a strong prejudice in favor of languages that can compute all computable functions, or decide all except all acceptable recursively enumerable sets. That's one. Well, if problems are Turing complete, this means if two different languages are Turing complete, this means in some sense there exist translations between them, even if only by means of the existence quantifier. It may not be an efficient or even an effective translation, but they exist. And that makes it hard to compare, to say one language is more powerful than another, because they both can compute everything. Another relation to understanding expressivity is very often you can write Lisp and think Prolog, or you can write Prolog and think Lisp. Because you can efficiently simulate the one language by the other. And it again makes it hard to compare the efficiency. Now, the approach of this work is to say, well, let's give away the gold standard of Turing completeness. Let's gradually look at simpler languages until we get languages that are no longer Turing complete. If the languages are not Turing complete, then we have many languages, so-called sub-recursive languages in complexity terms. And they've been studied a lot using complexity theory. And this is what P and NP and these many different complexity areas are about. And complexity theory is nice here because it does give some definite statements about things that can or cannot be done. And it's very different style from the programmer saying, this is impossible because I tried it this way and I couldn't make it work. You've heard that excuse many, many times. But to say that something is definitely impossible means there is no program, and it requires a different order of thinking. So the question is, does the programming paradigm affect the problems we can solve or the efficiency of the programs that we can write to solve them? And to do this, we need ways to formulate and understand questions about expressivity. The main thing I've been studying in this paper is something that in these slides I tend to refer to by more than one name. Like they say, love children have many names. But one way of saying it is one I frequently use is cons-free or read-only, and are basically referring to the same thing, where a program has a certain amount of input. It can look at the input, but it cannot allocate auxiliary storage. So there's no cons operation with nothing to create a new structure, and so sometimes read-only. Apologies, I should go through and clean up the terminology, but at least read-only is what I'm talking about. And in particular, we give some pretty nice characterizations of the relative computational power of cons-free programs. On the one hand, giving them different orders of data. Like a usual first-order program just has atomic data, zero-order data. A second-order program could have first-order functions as arguments, and so forth. That's just the usual terminology. Data order is one thing you can classify programs on. Another thing you can classify them on is what kind of control structures do they have? Do they have? Is it imperative, which would be tail recursive? Is it general recursive? Is it primitive recursive? Programming using only pulled right, as many functional programmers would say you should do. And so this is another dimension. And finally, this last thing is talking more about what cons-free means. And in this paper, the value that a variable can have can be a cursor on the input. It could be a pointer saying where we are on the input. And if it's a higher order, it could be a function from values. Yes, please feel free to ask questions.
So is it a transducer of some sort, or is it finite because it's finite state, but it has an infinite stream as input, or unbounded?
Yeah.
How will you think of this?
That's a good, that's a natural question. It's not like a finite, the simplest example in those terms would be like a two-way finite automaton, where you can have a cursor that looks at different places on the input. So I'm not really interested in infinite behaviors. I'm only looking at terminating programs. And communication is far too hard to say anything sensible about here.
Is Datalog const-free?
What?
Is Datalog const-free?
Basically, yes. I would.
But it has the power to create auxiliary tables.
Mm.
Okay, you're putting me on the spot. I'm not familiar enough with Datalog to give a good answer for that.
Well, so the point in the analogy with languages would be that they control the program itself creates data structures implicitly. Say if you were creating a sequence of closures.
Yeah, that's the focus here. Is on I'm looking only at programs that are not creating. They don't have something or cons. If you can create a new table on the fly, that would not be in the category I'm talking about. And frankly, it's too long since I've looked at Datalog to give a sensible answer to what you're saying. Let's move forward a bit, and then you can, if there are things that if you're still puzzled, you can bring up the question again. Yeah. Okay. Now there are a few results already existing. For example, on absolute expressiveness, that programs with first order data are strictly more powerful if they have general recursion than if they have only primitive recursion. And why? Well, the first class turns out to be the problems solvable are exactly the problems solvable in exponential time. And the second class are exactly the problems that are solvable in polynomial time. Now, I should be clear here that I'm talking about programs that accept a bit string, a sequence of bits as input, and the primitive recursion is over the bit string. So it's not primitive recursion, as you remember from the old days, but it's a string-based, a string analog. In that respect, that primitive recursion accepts exactly PTIME. And was it maybe Jurevich that proved that? I'm not sure. It's in my references anyway. That's something about absolute expressiveness. About relative expressiveness, Nick Pippinger proved a very fascinating result that has not had many consequences, unfortunately. But he proved that for a particular problem, that a pure Lisp program without setcar and setcooter had to be at least log slower than an impure Lisp program that could build structures and then change them by setcooter. And he's had some very good reasoning there. It's just I haven't seen people that have taken this and gone further with it, but it might have been a Journal of the ACM paper, I think. It's in my references. And finally, the last thing, and one thing that comes out from this paper, is that there's been always this question, can recursive programs do more than non-recursive programs? Can you remove recursion removal? There were many papers about recursion removal in the 60s and 70s. And in this paper, in this context with the read-only programs, that can be done if and only if polynomial time equals log space. The problem, and that is a well-known, very hard problem that nobody knows an answer to. So while I'm not solving a lot of these questions, at least I'm showing they're equivalent to some other hard problems that other people have found difficult to solve. And so what am I meaning by a decision problem? Well, a problem will be, in this case, will be basically a set of bit strings. So just to abstract things away. So we're given a string of symbols, and the problem is a set of these, and the question is a membership question. Given X, is X in the set or outside of the set? If X is a set of prime numbers written in binary, then it's deciding whether or not the input is a prime number or not. And then for classification purposes, we ask, can this be decided in T of n steps, where n was the size of the input? So how do computation times grow with time? So in terms of, to make things simpler, I'm letting the inputs being lists of Booleans. There's no real loss of generality here. And letting the output be a Boolean as well. And that's just a convenience thing. So a Turing complexity class, the set of inputs accepted by a Turing machine would be a set of bit strings that if you give the Turing machine this bit string as an input, then it will eventually stop and answer yes. The input is accepted. And then there's the usual statements on when does a Turing machine run in a certain amount of steps or a certain amount of space. And then in complexity, there's a lot of work on the time classes and the space classes. And like P is a set of problems that are computed in time bounded by a polynomial function of the input size. So very well known. And here are some of the familiar classes. P is the class you've all worked with. LOGSPACE are problem solvable by manipulating pointers to the input, but without ever allocating storage. P-space are problems that are solvable with a polynomial number of bits of auxiliary storage. So that's getting to be a big class. EXP-TIME is something that looks like it's a still bigger class. And there's this well-known hierarchy. And one characteristic of this hierarchy is that nobody knows whether it is a proper hierarchy all the way up. Nobody knows whether LOGSPACE equals PTIME, or whether PTIME equals PSpace, or whether PSpace equals exponential time. The only thing we do know is that if you skip 2 levels, there's a difference. That PSpace properly includes LOGSPACE, or exponential time properly includes PTIME. So in some sense, complexity theory is a theory of bad excuses, of giving explanations for things we would like to be able to do, but haven't been able to do. But they've been around for a long time. So at least it looks like these are some hard questions because some very good people have tried to answer them. And as one old slogan goes, that if you can't solve your problems, then at least classify them, which is... Now, this, I'm not going to go through all of this, so you can relax, but basically, we've got a matrix here. Along the top, we have the order of the data as to whether the data are just things that cursors can look at, which would be like 1 bit at a time, or whether they are functions from these, or whether they're second-order functions. And then in the limit, it would be accepted by programs at any number. And of course, anything worth its salt is Turing complete. So the top line is you always get here I've used what's now an old-fashioned terminology, recursively enumerable, which I think people will call computably enumerable nowadays. the mathematicians have done a lot of work with primitive recursion. And the programs that are primitive recursive, if you allow higher order functions, we end up with system T, which Gödel did in his day. What this paper, this JFP paper was about in around 2000, was largely about these read-only programs and then expressing their power in terms of complexity classes. And these are exact characterizations. That a problem is solvable in PTIME if and only if it's solvable by a read-only program without functions as arguments. And so these are not, it's not just descriptive information, it's exact characterizations. See? So we can kind of wander around this, and like this comment that recursive programs are more powerful than imperative programs. Well, they are if you have a first order data, because with first order data, the recursive programs decide exponential time, and the imperative programs. Let's see where. I'm sorry, my explanation got out of sync with my slide. Try again. If you ask, are recursive programs more powerful than imperative programs? Then what we're comparing is a read-only class against a tail recursive class. And that is actually, I think I've written this wrong, or else let's look at the bottom line. I'm confusing myself on this last line. For programs with first order data, general recursion accepts can decide any exponential time problem, whereas a tail recursive whereas a primitive recursive program, a program written with only folds, accepts polynomial time. Yeah, okay, so there is definitely a difference here. And so that was comparing general recursion with programs written in the approved style with only folds for the recursive definition.
Sorry for asking, but sure. I missed, what is order 1 and order 2 data? Is that closures or function spaces?
Right, yes. Order 0 would be no closures. Order 1 would be have closures that represent functions from order 0 values to order 0 values. Order 2 would be to have a value that represents a higher order function, a function that produces a function as a result. So this is saying how much power do you get by being able to.
So that's to answer the question whether you get more power from having closed functions, higher order.
Right. Yeah, and that's one of the punchlines of this thesis is that if you don't restrict the order at all, you can solve all the elementary problems. Elementary is one of the most misleading terms I've ever heard, but the mathematicians devised it, and it's problems that are computed in time 2 to the 2 to the 2 to the 2 to the nth, where the stack of 2's can be any finite stack. So that's what the mathematicians call elementary. Okay, and I think the main punchline at this moment is this nice observation that the entries in this matrix correspond to things that we're familiar with from another context, from the complexity theory. And so the matrix is defined by syntactic restrictions on programs, how they can be written. And yet what the answer is it's some actual limits on the computational power. Yes.
So was there a difference between, let's say, EXP space and EXP2 space?
Okay, sure. This is the number of bits you can use as 2 to the Cn, where n is an input, and this is you're allowed 2 to the Cn. Yeah. So and so forth.
So typically, in the recursion theory books, or textbooks, I learned that I can take any tail recursive function and turn it into a primitive recursive function. But that's not true.
No, that's not. I don't think that's true. That you can take any tail recursive program and convert it to a primitive.
Clearly, it's not true. So
maybe in the first line, read write. When you have read and write, probably you can do it. But you limit to read only. So the idea here is to limit to not look at the whole class of Turing complete languages in order to get that hierarchy, right? So if you restrict to read only, then you get that.
Yeah. Okay. What you were saying was a result that every tail recursive program could be converted to a primitive recursive program, and I think that's true if you're talking about a Turing complete language. That you could take the tail recursive program, assign Gödel numbers to all of the values, and then use primitive recursion. But that would make a big explosion in time and space. Yeah. So what I'm trying to stay within the realm of reasonable programs, and I don't like arbitrarily large Gödel numbers. I'm enough of a programmer not to think of that as a primitive. Whereas the recursive functions people do, and they had good reasons for doing this back in the 30s even. But for computer science, this is a little more. Yeah, and I think some of the other slides are kind of more explanations of some of these things. The program syntax, I think you've already got it. The program is a set of recursive function definitions, and what's on the right can be, you can have an application, if then else, and if it's cons free, then you cannot have E1 cons E2, but otherwise, it's okay to allow pairing and contraction because they're static operations. But a list which has an unbounded length can quickly get you into trouble. And that's just talking about my syntax, which you obviously understand enough to. There's no need to. And semantics values are closures, and a closure is a function name plus the values of any free variables of the function. And so this is all standards. It's a call by value, but higher order language framework. So all of these things in the matrix make sense, are talking about the same language, but just with additional restrictions on the type orders and of the data, or the control order of what kind of recursion you can use. And there's nothing here any of you is not familiar with. It's just, you know, the order of a function type is 1 plus the order of the argument type matched with the order of the result type. And this is absolutely standard. There's nothing unusual about it. But so a first order program by usual terminology is one with 0 order data. There can be maybe many variables, and we're talking about a list of variables, but they're all regarded as 0. And yeah. So let's see. The time is. We normally have about an hour for a talk, so I have about 15 minutes. Okay, so I'll skip over a lot of ugly details, but I can just say that the proofs of these statements are simulations. In the one case, simulating a program by a space or time-bounded Turing machine, and in the other case, showing that limited Turing machine can be simulated by one of my read-only programs. And there's lots of ugly details which are best studied offline. One of the results I think that is kind of neat is that tail recursive programs, I think you were asking about tail recursive programs before, they essentially, they've got as input several variables, each of which is a bit string, and a cursor on it. They may have any finite number of cursors on the input bit string. And they can run by moving these cursors back and forth. And this is why they're not finite automata. They're two-way, multiple head, non-writing finite automata. And believe it or not, Steve Cook studied this problem back in 1972. And in some respects, what I'm describing here is just a programming language version of what Steve Cook did way back when. Well, the essential point is that if you're given a string of bits, then the way our syntax is restricted is that if you have f of x, y equals something, then x and y are both going to be suffixes of the input. So you begin with like f0 of input equals and then some expression. So that's what your program looks like. So the input is the thing that has length n. So that's a sequence A1 through AN. And then what this can do is it can call f with the tail of x and the tail of x. And the tail of x, that's the string beginning with A2, and the tail of the tail is the string beginning with A3. So all the variables are suffixes of the input. And that property means that you can represent them by just saying how many bits are there to the end. And that's a log n bits. Log n bits is enough to say how far are we from the end. So you can represent a store in LOGSPACE. And that's the thing that gives the results, is that a tail recursive program with order 0 data can be simulated in LOGSPACE. And you can go the other way around as well. So this paper is full of little constructions showing a program of one sort can be simulated by say a Turing machine of another sort, preserving the balance. If you have tail recursion, suddenly the game gets a little bit different. The result for tail recursion is that you get PTIME. That read-only is the read-only class is identical to the problems that can be accepted in PTIME, and this is one of these places where Moskobakis has more expressive power than Gurevich has. Now that Gurevich is not here, I can talk about him. but essentially, if you're looking at read-only imperative programs, then they characterize exactly LOGSPACE. If you're looking at read-only programs with general function calls, by general function call, I mean say that f of x, y is, say, g of x, h of y. So you can have a call inside a call. That would be a general recursive call instead. That they can do more. Well, maybe. If PTIME is bigger than LOGSPACE, nobody knows whether it is or not. But at least, if we haven't solved our problems, we've classified them. And the actual proof of it is a little bit tricky. And one of the very annoying things is that these programs that characterize PTIME can actually run in exponential time, and for dumb reasons. The dumb reason, for example, here, f applied to x's can call f a tail of x's twice. And if it calls it, and then if you do your usual recursion analysis of what's the running time, you get that time t of n equals 2 times t of n minus 1. And so it looks like it's running an exponential time. But of course it's not, because it's a function. So it will produce the same value both times. And that's the solution to get around it, is to use a what I call a memorizing simulation, that if it computes a value, it remembers what it was. And then if later on it tries to compute the same value, it first looks it up in the memo table, and if it's there, okay. And it turns out that does preserve polynomial time. It can do something. It can maybe square the time, or it can make it a bigger polynomial, but it'll still be polynomial. And there's okay.
So is there bottom-up evaluation?
Yeah, you could certainly do it bottom up, because you know all arguments are always suffixes. So you could just decide in advance, I will produce a set of possible values for all suffixes and let the table be empty at the beginning, then gradually fill it in. Yeah, that works fine. Yeah, that's just a matter of programming style, but it's a programming style that doesn't seem to make a difference asymptotically. And the results the other way are messier, because they're involving showing that programs can be simulated by Turing machines of different types. And for that, it seems you have to resort to coding numbers. And once you do that, you get the kind of ugliness that only recursive functions people are used to tolerating. Stephen Claney could have dealt with it well. I've tried to do a responsible job of it and defined what I've called a counting module, which is a systematic way of manipulating a set of numbers that is bounded within certain bounds. And let's see. Yeah. So what I've been describing as sort of sketching out is this top row. Well, I'm very, very satisfied with this pretty matrix, lots of results, nice long paper, good number of citations. And then this spring, a postdoc at Copenhagen comes up and changes the game completely. What she was doing was saying, well, what happens if we let our programs be non-deterministic? Well, of course, one thing is that they're not functional anymore, because the output is not always a function of the input. But it makes sense. If you think of a non-deterministic finite automaton, it accepts an input if there is a sequence of transitions. And so the idea here is you think of a const-free non-deterministic program. It accepts an input if there is a sequence of guesses. And so the only language extension to add is to say that an expression could be choose of either expression 1 or expression 2. So syntactically, it's rather trivial. It's just saying if you're given certain bindings of the variables, you non-deterministically choose either the one branch or the other branch. And of course, what she was expecting and worked hard on for a long time was showing that you would get NP time, NEXP time, NEXP squared time, and so on. That's the sort of thing you normally expect. If you add non-determinism, you just make the classes non-deterministic. Well, there turned out to be two problems with that. One was that you didn't get NP time, you got P time at the first level. And intuitively, the reason for that is that if you're finding, say, a shortest path on a graph, that you can do this non-deterministically. You can take a drunkard's walk, but you can also do it deterministically by leaving a trail of breadcrumbs and systematically taking all walks. You don't have to do polynomially many walks. Try again. You don't have to do exponentially many walks. Polynomially is enough. So that problem can be solved in deterministic polynomial time. That's essentially the same reason here. The big surprise is that all this pretty hierarchy here suddenly jumps up to the biggest class immediately. And so it's saying that non-deterministic programs, if you even allow them to have first order functions as data, they can do a lot more than deterministic programs can do. And how it's proven is by some very clever non-deterministic programming. In fact, I would go so far as to say more than clever. It's mind-boggling. I at first did not believe it, so I ended up writing some programs and trying things out, and lo and behold, yes, it did work. The first version was shown to be convincing by using a random number generator instead of in place of non-determinism, and just finding enough runs to be able to get the proper answer. And I wasn't entirely happy about that because the two are not really quite the same. But since then, in fact, on my last leg on this visit, with the Alpesen people from UCLA, they wrote a monad for Haskell that could properly treat non-determinism and collect all the results. And what she was doing seems to hold together also on the operational level. And so that's what's happened. There's been a paper on it in the European Symposium on Programming this year, and she was working with Jakob Grue-Simonsen, whom you probably know. Somebody at DECO that you probably know. Jakob Grue-Simonsen.
Oh, yeah.
Yeah, so that's basically, that's all that I have to say. But it's trying to fit together questions about programming languages with things about complexity. Oh, and the usual summing up slide. But I do have some extensional results only because the complexity people have extensional results. There are some proven differences. There are some results about some problems of interest to non-specialists. And then this last one was this thing that startled me this spring. We're only talking about read-only programs, so your comment about primitive recursion, I think, is because it's in a different category. I'm saying absolutely nothing about concurrency. And finally, this last point is that memorization allows you to resolve this paradox, or what looks like a paradox. It's not really one. Okay, that's it.
Some time for questions.
It's almost like bugging you about data log again. The result on data log, query complexity, I guess it's called, is that it characterizes PTIME.
Yes.
The data log characterizes. Yeah. And that seems deceptively similar to the non-deterministic read-only results, which is also PTIME.
Okay, yeah.
So non-deterministic functional read-only program on order 0 data is that fundamentally different from say a data log?
I think we're asking different questions here. Well, I'm not 100% sure of it. With data log, you're asking for the set of all tuples of arguments that satisfy a query.
No, you ask whether there is feasibility of the query.
Feasibility.
Yeah, whether there exists a tuple.
Exists a tuple, and once the memorization table has
the
function.
memorization is at the bottom of data log.
Yes.
And So I'm trying to understand whether the results will.
It's a good question, and I remember a few years ago being very inspired by a series of Annie Liu's papers where she was developing efficient algorithms by expressing them in data log terms and then doing smart implementations of the data log terms. But that's been long enough ago, and my memory is fuzzy enough that I can't give a good comparison of that with this. But you're right, it's a good thing to look at and check again. Of course, she was looking at one problem at a time, and I'm looking at frameworks of sets of problems. Mm-hmm. But that still, what she does could be very relevant. And there, at least, I would see much more data log to give a more realistic answer, but I can't give you an answer now.
But fundamentally, you are able to write data. It's just you write to variables, right? Mm-hmm. Not you don't create heap. So right, you can write to a global variable, and you can write to locals, mm-hmm. And there should be some simulation of that data log.
Yes, I wasn't asking clarification questions more often. But anyways, what triggered me?
Yeah, I'm still trying to wrap my head around exactly why this happens and getting a more. I believe now that it does happen, and I can see her construction that if she has a counting module that can count up to f of n, then with Albertson nondeterminism, she can produce a counting model that counts up to the f of n. And so implicitly, you're getting a lot of extra storage. And you can't get that storage in my framework because it's deterministic programs. Mm-hmm. When you leave a function, you've lost every information about it. And that's my intuition is that somehow the nondeterminism is allowing her to guess random bits. And the fact that they're higher order functions mean that you can remember those guesses. But there's more to be understood. When William asked me for an abstract to give a talk, this was right on top of my head. So apologies for the very theoretical talk.
So I remember a result by my supervisor back in Oxford, where he had this hierarchy of the exact same hierarchy, in fact, PTIME, X time, XK time for decidability of initial logic over high order over trees generated by...
Who was your supervisor? I didn't hear.
Luc Hong.
Oh, Luc Hong, yes.
So generated by high order recursion schemes. And so my question is like, is there, because now you show that there is this clear way to prove that the language, program belongs to that particular hierarchy of classes, is there maybe a way to rewrite those proofs by just showing that this particular problem can be written in that using that syntax and constraining the order of the higher order parameters in the same way, so you can get the same result, but without having to do without having to prove it yourself.
It would be nice if it were true. I found it difficult reading Hong's work to see the programs lying in them. And so I think the hard place would be simulating a Turing machine of a certain complexity by the formal objects he was dealing with. And I'm not saying he's wrong, but I'm saying that he's building on a bunch of complexity results other people have shown, and you don't see the constructions in Luc's work. Rather, you just see him reducing his results to results that other people had done. And I haven't read enough of those other results to give you a good answer.
Maybe all the problems that, not necessarily this one, but I also produce the hierarchy of classes, of complexity classes, E time, X time, X2 time. And so maybe all those proofs are actually all the same instance of this hierarchy that you just showed here, where...
Yeah, Yeah, I've had the feeling on this paper that I was understanding something real. There was a phenomenon there. And my first conceptual ideas were that the order of the data determined the size of the bit bucket. That you got a bucket full of bits that's describing the state of the program, and as you went to higher order programs, you got bigger bit buckets. And that analogy worked at least for the deterministic programs, but for the non-deterministic, it seems to be clever programming is expressing it, and it may be a sign that my definition of non-deterministic comes free is not a good definition. I haven't. I'm not clear yet as to what the problem is, but the back door is that you can simulate cons without having cons by higher order functions, and the lambda calculus people have known this for a long time. But the price has always been that you increase the order of the objects you're working with, that the data objects have higher orders. And so in one sense it's not surprising, or in another sense it is surprising that what I thought was a finished body of work suddenly turned out not to be.
I would say I found this really exciting in a way, because I'm thinking about all the challenges we see with very large data sets. So for instance, over in the web search world, it's not uncommon to have 40 petabytes of data for lunch, you know. And having this kind of rigorous result on the syntax, and sort of being able to syntactically say, okay, this is something that characterizes LOGSPACE, is very nice, because then we could imagine a system that sort of checks syntactically and says, oh, this query is probably going to terminate today, or it checks syntactically and says, all bets are off. This might terminate next week or next year or who knows what. And that's a very real issue today, because we actually have queries today that people have written that are just going off.
They're still running.
Still running, no one knows when they're ever going to come back. And so being able to have this kind of clear syntactic mapping between like the characteristics of the query or the program I write and like the complexity class is just really exciting to me. So thank you for bringing this forward.
Thank you. I think Messier had some results about complexity and queries relating to syntax, and I have a feeling that it's in a similar family to what I'm doing here.
Absolutely. Yeah, but what I like about this is now I can use your work and say for an arbitrary kind of programming language, I don't have to be related to just SQL or something like that. I can say, okay, look at this. Does it have order 1 data, order 0 data? Does it have read-only? Does it, and a lot of these programs are read-only. So
I should guess. Have to be, because you don't have a memory that's big enough to deal with.
Well, it's not possible, Thank you.
Okay, thanks.